Start ಮಾಡಿ. Hello students, welcome you all for physics session. Well, dear students, in last class we have discussed about electric potential energy for a point charge, two system of charges, and for an electric dipole. Now move on to the chapter begins with charge, electric potential, how the potential concept existed, how the electric potential energy can be utilized. So after all this, in the first chapter we discuss about charge. Later we will end for potential, and then we move on to potential energy. Okay, the one curiosity question will arise is that yes, we have charge, potential we have, force we have, electric field also we have. Okay, so with having these all things in our hand, what are we doing exactly? Where we are using this? So for that question, answer could be the capacitance or capacitor. Students, we know all exactly the meaning of the word capacity. What do you mean by capacity then? Capacity is a term we are using to express the ability, the storing capacity. Okay, so though we are using the word capacitor, now of what? Ability of what? Capacity of what? Capacity of keeping charges or charge. As you know, we have positive charge and as well as negative charge, and we know the motion of positive charges and negative charges. We know the motion of electric field lines for positive and electric field lines for negative, how they radially move, radially outwards, radially inwards. If suppose I consider in any planar surface, charge is plus q charge is there, minus q charge is also there, and if suppose I kept plus q charge and minus q charge togetherly, there will be current production will be there, and the current production will study in third chapter. Well, now move on to discussing on capacitor. Capacitor is a device where it can store charges, it can store electrical energy, and wherever the excess charges we have, we are supposed to store it in the capacitor. Now, so studying the capacitor, we will have multiple devices, multiple orientations of the capacitor. In that particularly, most commonly, most famously, you are using parallel plate capacitor. Okay, the name itself is suggesting us where we have a plate of conducting material and we are storing the capacity, we are storing the charges. Where? How in the nature? And the two, those are in parallel. Nothing but parallel indicates minimum we require two over here. So the arrangement of parallel plate capacitor will be in this orientation where we have two conducting parallel plates where we are storing at one side positive q charges and negative q charges, such that these two parallel plates are separated by some distance, and this separation is consisting of some amount of dielectric medium. Dielectric medium. When a very certain question exists is that, why sir, why you are keeping plus q charge and minus q charge not in together way? We are kept these two parallel plates in a different way where we have placed a dielectric medium. Very curiosity question existed is that the simple funda is, if suppose you kept these two together such that very minor distance is there will be chance of a segregation of charges, vice versa. They move from here to here and there to here. So to avoid this, we are having parallel plate arrangement where in that gap we are substituted dielectric medium, and you already know that medium plays a very important role here. Why? Because depending on the medium we are going to deciding the epsilon permittivity, medium permittivity. Nothing but we require the permission of that particular medium here, so that our charges, our electric field lines can move easily. Okay, so depending on the dielectric medium, parallel plate capacitor capacity variously depends. Okay, now move on. So move on to definition of parallel plate capacitor. Arrangement of parallel plates where conducting material are substituted which are separated by some dielectric medium, and this dielectric medium we were discussing in the last class about the dielectric medium. Okay, so dielectric medium is a medium where it can transmit the charges without conducting, such as S2O, N2, O2. So these are all example for the dielectric medium. So you may ask me, sir, suppose we place a different kind of medium such as air, how about the charges? Charge segregation will be different. Why? Because each and every medium has different absolute permittivity medium value. Okay, now move on to, so this is all about the capacitor and parallel plate capacitor. Now we'll go for how the charge capacitance exactly depends. Now, as we have discussed the electric potential here, so we'll use the word V, where V indicating electric potential. And then when you are going to study the nature of the electric potential, this electric potential is directly proportional to charge Q. So as the number of charges you are increasing, nothing but you are increasing the electric potential of that particular point. As you are decreasing the charges, you are decreasing the electric potential. So these are in absolute, directly proportionality condition. Now, so anyhow we have a proportionality condition here, we have to get it into equality. So this conversion is requires a direction. That particular direction is nothing but to avoid this proportionality, to make it to equality, we need to substitute here some proportionality constant, and that proportionality constant is called as C, and that will be 1 by C. That will be inversely proportional. Why it is inversely proportional and why the charges are directly proportional? That is the thing we are going to learn now. Okay, now move on to see here. As we have the equation, V is equal to 1 by C into Q. So I am now allowed to write C is equal to Q by V. Okay, or else I am write here Q is equal to V into C. So well students, this is the one formula I keep you people to remember always, that is Q is equal to V into C. Yes, it is true that V is equal to Q by C. C is equal to Q by V. These are the standard formulas, but I prefer you people to keep remember this formula Q is equal to Vc. Why I will tell you. So in physics we have so many formulas, so many concepts, so many definitions, and it's quite difficult to remember all the formulas. To keep remember the formulas in physics, we will do little bit of fun with using a short forms. Here I have a term Q is equal to Vc. Vc, we can prefer the name vice captain, right? By keeping the vice captain simple definition or simple statement, we can remember the whole funda. Q is equal to V into C. If suppose you remember vice captain, there will be charge term, there will be potential term, and capacitor or capacitance. So we'll define the term once again. So C, capacitance of a capacitor. Q, charge placed in a capacitor. V, potential of that particular capacitor. Okay, now so depending on this thing, one very important formula or definition we need to define here, that is, keep remember, capacitance of a capacitor can be measured in terms of SI unit, and that will be Farad. The SI unit of capacitance of a capacitor is Farad. Okay, now move on. So how one can define 1 Farad? Quite simple. Here we have the formula C is equal to Q by V. What you are requiring here exactly? So my aim is to get only 1 Farad where I have a charge Q, where I have potential V. So nothing but I need to alter the Q value, V value, so that I can get capacitance of the capacitor will be 1 Farad. So what I am supposed to do? I know charge SI unit will be coulomb, potential SI unit will be volt. So what I am supposed to do here? Simple thing I need to do to get 1 Farad is to have 1 coulomb charge. So I will write here 1 coulomb. I need to have 1 volt of potential. So 1 coulomb is there, 1 volt is there, nothing but capacitance of a capacitor will be 1 Farad, isn't it? Now, so how to define 1 Farad definition then? So when does the capacitance of a capacitor is said to be 1 farad? Simple definition. We need to answer is when do we have a 1 coulomb of charge which is of 1 volt potential difference in a parallel plate capacitor. Now the capacitance of the capacitor is said to be 1 farad. These are the definitions which are related with the capacitance of a capacitor. Okay. Well, now we'll go for next segment of today's discussion. That is capacitance of parallel plate capacitor. Okay, now, so what we are doing, what we did exactly in the last session, few minutes back, we just defined the capacitor, definition of capacitor, and parallel plate capacitor. Yes, we have spherical capacitor, parallel plate capacitor, cylindrical capacitor. So capacitor is just nothing but a device where we can have two terminals. Okay. Now I will show you diagrammatically, not exactly in portion. So this is how it looks like, where we have two terminals, and it will be coated with some amount of dielectric or insulator kind of material. Okay. Keep in mind this thing. And suppose we have a parallel plate capacitor, cylindrical in a cylindrical way. Also, we can get a capacitor. So these are the and one more thing we have about sphere. In spherical nature, we can have this one. In cylindrical or in hexagonal form, and most normally these are of parallel plate capacitors, where one plate is consisting of plus Q and another plate is consisting of minus Q. Now move on to what exactly the formula requires for to measure capacitance of parallel plate capacitor. Okay, now so for that I need parallel plate capacitor over here, and so these are the two conducting metal plates. Let us name these as M, plate M, and let us name it as plate N. So this is M, this is N. Okay, move on. As we know, charges or electric field lines will move from positive to negative. So this direction will be in this way. Keep remembering this. If suppose we may take the between the plates or outside the plates, this direction won't change at all. Keep remembering this point. Because we have studied the electric field lines and electric field, what is that? Positive point charge and negative point charges also, how they are moving radially. Okay, move on to. So plus Q charge you have, minus Q charge you have, nothing but there will be transition or there will be transition is going to happen now. And they are separated by some distance. Yes, and they have certain area. Okay, now move on to. So depending on this point, keep remember the vice captain formula. Q is equal to V into C. Move on to. So if suppose I want to calculate the charge density, sigma is equal to Q by A. As in first chapter we discussed about the charge distribution. Charges can distribute through linearly, area, value. So they can move in a linear, one dimensional, two dimensional, three dimensional, in a many dimensional format. So as you know, Q is equal to sigma divided by A. Okay. So I just took the total number of charges, charge density. One on the other, SS charges are done. Move on to. So I particularly choose one reference point here. Is that what exactly the charge density outside the plate M? Okay. And there I will go for what are the number of charge density outside the plate M. And then I will go for what is the total number of charge density between the plates. Okay. Now move on. First point I want to clear for charges outside the our charge density outside of M plate. Okay. Now move on. Now as you know, Q is equal sigma is equal to Q divided by A. This formula we know already. But what happens here outside the plate? When we are considering outside the plate, charges are supposed to move. Yes, few minutes back only I said that charges will move from positive to negative. So look at the direction over here. How they are moving? Isn't seems that they are moving in opposite direction. And as we know, if suppose they are moving in the same direction, we will take in mathematical form. Plus, if suppose they are moving in outside, I mean to say opposite direction, we will take minus sign. Right? Now move on to. So if I want to calculate the electric field, so I need to get sigma divided by 2 times of A. or else I may took it as 2 times of epsilon naught. This is the electric field when you are applying the Gauss law. Certain media, certain place, certain area we have here, closed surface is there, so that we can calculate the electric field outside the plate M. Move on to, yes, they are moving in an opposite direction, so sigma divided by 2 epsilon naught. What happens here? They cancel out. What left it here? 0. Isn't it? And move on to the second very important point here. Outside of N plate. Okay. Now move on. What happens here? Yes, when you are looking at the N plate, they are also moving in a different direction. I need to get the same thing, no? Sigma divided by 2 epsilon naught minus sigma divided by 2 epsilon naught. What happens? They cancel, so what happens is 0. So meaning of expressing these two statements in this direction is very simple, that we have taken the total charge density outside the plates also and inside the plates also. But because charges can move in any direction. Charges can move in particular direction with related to these two parallel plates. Isn't it? And move on to, finally we move for third point, that is in between the parallel plates. So when you are taking out the in between plate direction, how they are moving now, tell me. Just think on it. We have taken the outside plate region. We have taken the second plate outside region. Now we are concentrating on the inside. Nothing but they are in a particular dielectric medium and they are supposed to move in a restricted direction. All the charges have to be moving in a same direction. They will not go in a random direction or opposite direction. And because of this thing, here we have taken a minus sign, but here we will take a positive sign. So electric field is equal to sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught. What will we get here? Sigma by 2 epsilon naught plus sigma by 2 epsilon naught is nothing but sigma by epsilon naught. Now you may ask me, sir, why did you take sigma divided by 2 epsilon naught and sigma divided by 2 epsilon naught? What is the total charge density Q by A? What is the electric field formula through Gauss law? Sigma by epsilon naught only. But they are separated in a half portion, no? So we have to take it as 1 by 2, 1 by 2, half. And though here also we have to take it as 1 by 2 and 1 by 2. Now move on to, so we have just taken the electric field formula. Okay, now move on to, okay, now, so we have considered the electric field in between the plates. Outside the plates when you are going to vanish out, and only vector thing is E is equal to sigma divided by epsilon naught. And you already know that, what do you mean by sigma? Charge density. Q divided by A, I will take here at the bottom side, denominator Q divided by A into epsilon naught. At the same time, here we are using the electric field term and electric potential term. Nothing but I should not forget the relation between E and V. That is relation between electric field and the electric potential. So what do you mean by relation between E and V? Very simple is that electric field E is equal to dV divided by dr with a minus sign. We are just considering, we are concentrating only on magnitude. So minus sign has to vanish out. For my reference sake, I will take dV as V, and if distance dr is there, I will take it as d. So nothing but the very well-defined formula, the relation between E and the V will be E is equal to V divided by D. See here I have taken the D term as a distance. You may take it as R, you may take it as X, whatever you do. Okay? Now move on to. So there I have the formula E is equal to Q divided by A into epsilon. Here I have the term E is equal to V divided by D. And move on to, here I am allowed to write V is equal to E into D. At the same time, what do you mean by E? Through that equation. So that is the electric field between the parallel plate of a capacitor. Keep remember that. And now move on to, so I just substitute Q into D divided by A into epsilon naught. So I have a formula V is equal to Q into D divided by A into epsilon naught. Are you getting the formula? If suppose we have this pause the video and just play back and get into the action. Okay na? Now, so just I will modify the term so that I can get my required form. Okay. So what I have here, V is equal to Q into D divided by A into epsilon naught. Okay na? Now move on. I'll just modify the term. V divided by Q is equal to D divided by A into epsilon. Right? What I did here? I just shifted Q so that it can become V by Q. So in a cricket, captain left it out. Now let us say captain is hurted. So who is that person is going to be in action? Vice captain. No. Let us recall the vice captain. What do you mean by vice captain? Q is equal to V into C. Vice captain has to be in action. Now, so what I can write here? Q divided by V is equal to C. No. At the same time, what I have here? V by Q. So nothing but V by Q is equal to 1 by C. Isn't it? Now, so what I have the formula here? V by Q is equal to 1 by C. Here I have the V by Q. So V by Q is nothing but 1 by C equals to D divided by A into epsilon naught. Shift the formula. C is equal to epsilon naught A divided by D. So this is the amount of capacitance of a capacitor. C is equal to epsilon naught into A divided by D. Okay na? Now, so as I mentioned very earlierly, is that we have the particular dielectric medium. We may write here instead of C, Cm. Nothing but capacitance of a capacitor in a medium, of that particular medium. So I will repeat the terms once again. C, capacitance of a capacitor. Epsilon naught, absolute permittivity of that medium. Area of that parallel plate capacitor. Distance of separation between the two parallel plates. Okay na? So this is the formula we must know to measure capacitance of a capacitor. So you may ask, and suppose we do not have a particular medium, but we have a dielectric medium. So what happens there? So when do we have a dielectric medium? Formula will change into action is that C is equal to epsilon naught into K into A divided by D. What I did here? I just place the term K. What do you mean by K? K is a dielectric constant. So this will be for air medium and this will be for particular dielectric medium. So for reference I will take here A, Ca. Ca indicating air medium. What do you mean by M? Of that particular medium. Okay na? So one very interesting point I need to know here is that here only I will do it. See here. Students, here I have the formula for air medium. Here I have the formula for dielectric medium. So nothing but I can get the relation between air medium and the dielectric medium through these two expressions. Very simple thing, right? We'll do Ca divided by Cm equals to epsilon naught into A divided by D whole divided by epsilon naught A into K divided by D. What happens here? D cancels up. Epsilon A cancels up. What left here? Ca divided by Cm equals to 1 by K. Okay. Now, so what I can write? K is equal to Cm divided by Ca. Right? So this is the definition for dielectric constant. So how to define dielectric constant then? So dielectric constant of a capacitor it will be defined as it is the capacitance of a capacitor placed in a medium to the particular capacitor is placed in a air medium. Is that quite simple? What capacitor you have taken for a medium, you should take once again in a air medium. You should not reverse or replace or any kind of or any other capacitor. What the capacitor you have taken for the medium, the same capacitor has to be taken for the air medium. That is the thing. Okay. Now, ratio of capacitance of a capacitor of a medium to the capacitance of a capacitor of a air medium. So, this is the definition of dielectric constant.